Good afternoon, everyone. Welcome to the second webinar for this week, celebrating the Cybersecurity Awareness Month, which is October. So we have another special speaker today who will be covering one of the hot topics in cybersecurity and also which is relevant to our day-to-day lives. Let me go through the profile of our speaker today and also into the details of his talk. So we have Dr. Mahdi Rabbani with us today, a postdoctoral fellow at the Canadian Institute for Cybersecurity. And before joining CIC, he was a visiting researcher at Dalhousie University, where he conducted research focused on ML and DL approaches for DDoS attack detection in IoT devices. He earned a full scholarship from Nanjing University of Science and Technology, majoring in computer science and technology, and graduated in August 2022. His PhD dissertation, titled ML-DL Approaches for Malicious Behavior Detection and Recognition in Intrusion Detection Systems. Prior to PhD, he completed his MTech in Artificial Intelligence at Mysore University in India. Mahdi has made significant contributions to the field of cybersecurity with a multitude of publications in various journals. His research interests are in AI for cybersecurity, malware analysis, machine learning, deep learning-based network anomaly detection and prevention, as well as privacy-enhancing techniques for IoT devices. So that's the impressive profile of our speaker today. And Mahdi is going to talk about enhancing generalizability in DDoS attack detection systems through transfer learning and ensemble learning approaches. Over to you, Mahdi.
Yeah, thank you very much, Wendy, for the nice introduction. Hello, everyone. As Wendy introduced me, my name is Mahdi Rabbani, and I'm a postdoctoral fellow at Canadian Institute for Cybersecurity. Today, I'm going to talk about enhancing generalizability in DDoS attack detection systems through transfer learning and ensemble learning approaches. So we will have an introduction to anomaly-based intrusion detection systems and also the current state-of-the-art data sets for intrusion detection systems, applying transfer learning for intrusion for DDoS attack detection, how it can help the traditional intrusion detection system for DDoS attack, how transfer learning can help. And also, we'll talk about data preprocessing and feature extraction in network traffic data. And meta classifier based on ensemble learning for DDoS attack detection and conclusion. So let's start with a background of what is the meaning of intrusion detection systems, and specifically anomaly-based intrusion detection systems is a security mechanism designed to monitor network traffic data and system behavior to identify malicious activities in a network. And there are different types of intrusion detection systems that like signature-based intrusion detection systems, anomaly-based intrusion detection systems, are also hybrid version of these two. But here at this presentation, I'm going to talk about anomaly-based intrusion detection systems. And unlike signature-based intrusion detection systems, which relies on known patterns of attacks, anomaly-based intrusion detection systems works by establishing a baseline of network traffic behavior and then flagging any deviation from this baseline as a potential security threat. And when the system detects activities that significantly differ from the established norm, it triggers an alert to notify administrator about the potential intrusion attempt. And also, this proactive approach helps in detecting novel or previously unseen attacks, enhancing the overall security of computer networks. So here is a scenario where like distributed denial of service attack happen in IoT devices, here you can see that here we can see there is a bot who is running the DDoS attack and remotely controls the IoT devices to launch DDoS attacks. And here there are like thousands and millions of IoT devices that these IoT devices are forced to use their resources, battery, power, connectivity, to send malicious requests in order to overwhelm the target servers. And you can see that there are many requests sent to the server, and when the legitimate user, they want to use this server, it is unable to access these services to those users. This is how DDoS attack, it's a very simple scenario where DDoS attack happen on a server, and it can cause a lot of major issues to the server, and also both IoT devices and server are the services and other functionality are targeting, and they are deactivated for a period of time. And so what is the what is the meaning of generalizability limitation, or what is the meaning of when we are talking about we want to enhance the generalizability in intrusion detection systems? What is the limitation of those intrusion detection systems that we are going to improve it? So there are some limitations, like such as limited training data. Anomaly-based intrusion detection requires diverse and representative training data to effectively identify novel DDoS attack patterns. Although when we are designing a machine learning based model for intrusion detection system, but it is still need, like, we have to update model like every like month or every week to like train the model based on the new pattern, which is new attacks. So here, even when we are training a model based on the data that is collected in an environment, so when it comes to another environment with which there are different type of patterns of DDoS, then the model may not be able to identify those patterns. And also, there are overfitting issues. So overfitting occurs when the intrusion detection system is trained on a specific data that does not accurately represent the broader network environment, and also generalization to new attacks, as I mentioned. Anomaly-based intrusion detection system may struggle to generalize to entirely new type of DDoS attacks that have never been observed in the training data, and also a scalability challenge. Adopting anomaly-based intrusion detection system for large and diverse network while preserving accuracy can be difficult, because from the collecting the network traffic data in one environment might be different with another environment. So when we train a model with the data that's collected in environment A, it may not be working as good as A in environment B. So environment changes can be challenging point for intrusion detection systems. And also network diversity. Anomaly-based intrusion detection may struggle to adapt to networks with difficult characteristics, affecting the effectiveness of diverse environment. So let's start with the transfer learning approach for DDoS attack detection. So I just want to mention some definition about transfer learning. Transfer learning is a game-changing concept in machine learning. It is about leveraging knowledge from one task to improve performance on another one. It accelerates learning, enhance generalization, as I mentioned, and adapt model to new challenges in building an existing expertise. So it's very simple. We have like two different data sets. We want to train a model in a data set, and we expect the model to work in data set B, which is destination data. So we want to see how we can transfer some knowledge from a model which is trained in dataset A, and we want to see how it will work in dataset B. So this is kind of measuring and checking how we can transfer little bit knowledge. It cannot be 100% knowledge transferring, but it might be like 10%, 20%, 30% of transferring the knowledge from source data to destination data. And also in this model, we employ transfer learning to harness the capability of pre-trained CNN combination of two deep learning approach, CNN LSTM model. And initially, the model is trained on dataset A, which is CIC-IDS 2017. And this model is adapted to the task of detecting DDoS attacks within the destination data. And we selected another data set for this, which is CIC-DDoS 2019. And also transfer learning allows us to transfer the knowledge and features gained during training on source data, specifically the train layer. We are concentrating on the hidden layers here in this deep learning approach when addressing the related problem in destination data. So now we have selected two different data sets. The first one is, as I mentioned, CIC DDoS 2019, which is specifically collected for DDoS attack. And the number of samples that we have selected is 200,000, which contain very less number of benign samples, around 1,751 samples, and also a very large samples for DDoS attack. And this dataset has 88 features. And for CIC-IDS 2017 dataset, this is an intrusion detection dataset. It has different type of attacks, but we selected just the DDoS portion of the dataset, which has like it's like a balanced data, like 97,000 benign samples approximately, and 128,000 DDoS attacks. And it has 78 features. As you can see, even with using transfer learning can happen with the two different data sets with two different features. You can see that here we have 88 features for the dataset 2019 and 78 features for the CIC-IDS 2017 dataset. And yeah, these are the features of all the features in 2017 dataset. There are different type of features from source IP, destination IP, some time-based features, flow-based features, some like additional features that is the researcher here at CIC, they use flow meter to extract those features from both header and the payload of the packets. You can see there are a lot of additional features that they calculated based on different measures. And now I'm going to start with the first one. We will have three different models. The first model is, as I mentioned, the CNN LSTM. It's a hybrid model of two different deep learning techniques. Here we use CNN for capturing specific features, and also we use LSTM to capture temporal dependencies. And the source of the data here is CIC IDS 2017. And the reason why we selected this data, because as you saw, it was like a balanced data. We have enough number of samples for benign and enough number of samples for DDoS attacks. So we try to train the model based on a balanced data. And so this data set has like both benign and DDoS attacks. And also it has, as I mentioned, it has 78 features and like this number of samples for both benign and DDoS. And also the goal is building a pre-trained network. We want to train the model based on these features and these samples. And this is the model, as you can see here, input features that comes from the features in a data set. And this is the CNN and LSTM. Here we have conclusion layer, max blink, and in the middle we have LSTM. We use bidirectional LSTM, and we have a fully connected layer, and with a dropout, and also we have a detection phase to identify DDoS attacks against normal ones. In a second model, which is a baseline model. So the model 2 is the same combination of the deep learning model, and also here we used the second data set, which is CIC at DDoS 2019, and as it has like 88 features. And also, as you can see here, we are trying to give an imbalanced data. Here, the number of benign samples is very less, and the DDoS patterns are too much. So, and the goal is having a baseline model for comparison. So it's the same model. And in the third model, which is we are going to use the transfer learning. So model 3, which is CNN. We didn't completely train the model. It is just using the pre-trained layer from the model 1. And also, so the destination data is CIC 2019. I don't want to repeat. So it's the same thing as model 2. But the goal is utilizing the pre-trained network to expedite the development of more efficient model for the detection of DDoS attacks. And here you can see that we are not going to train the model again. So we are directly using we freeze the layer from model 1, and we put it here to not train the model again. So let's now go for a comparison. So we have, there are two, as I mentioned, there were 3 models, but here we are going to compare model 2 with model 3. Model 2 without transfer learning, and model 3 with transfer learning. So as you can see that there are a huge difference between loss values. Here in the model 2 without transfer learning, the starting the loss value was 859, but the third model, it is just 48 because the model has already trained. And the training time, the third model is less than the second model. And you can see that the precision, accuracy, and recall also, we achieved better result in the third model with the transfer learning. So you can see that even a confusion matrix, this is for the model without transfer learning, and this one is with transfer learning. Although here the DDoS attacks here, it just there is just one misclassified error, but here with the benign sample we have approximately 200, but here the misclassification patterns are 35 for benign and 14 for DDoS. And this is some other evaluation metrics for both models. Now, there are some advantages of using transfer learning. So since we don't have enough time, I'm just going to just read the main points. So addressing data imbalance, utilizing similar task knowledge, and also reducing training time, and also loss functions. As I mentioned, it is very important in transfer learning because start with the lower loss function, lower loss value for the starting. Because yeah, I forgot to mention that with the first model is trained with 100 epochs, but the second model and third model, we just try to train the model based on just 2 epochs to see how transfer learning can be useful. So the second model that I'm going to explain is a meta-classifier based on ensemble learning for DDoS attack detection. And also we have classification of DDoS attacks here in this model. So the model is a meta-classifier model, and also we have applied like many processing and feature extraction techniques. And in the detection phase, so we are trying to identify DDoS attacks among normal patterns, and also we have another phase for classifying sub attack category, and also we use CIC DDoS 2019 dataset with 88 features. So there are different tasks that we have to do before training the machine learning model. We have data cleaning for removing duplicated data. We have to handle misvalues, and also we have some features that we need to convert. For example, protocol type, service status, and other things. We have to convert these like non-numerical features to numerical features, and also like there are different type of feature conversions or label encoding, one-hot encoding, but mostly we use label encoding in our model. And there are feature normalization and scaling. We have different type of features. Some of feature are between 0 and 1. Some of feature has value more than 100, more than 1,000. So since we want to calculate during the process of the training, we have, if we convert those, if we normalize those features, we will have a less computational process. So we normalize our features. There are many techniques, z-score normalization, min-max scaling, and also maximum absolute value. Depending on which machine learning technique we want to use, we can select one of these normalization techniques. For example, if we want to use, if we have a structure of neural network in our model, it's better to use a min-max instead of z-score. But for some supervised learning techniques like random forest, XGBoost, and also decision tree, it's better to use z-score normalization. And we have feature selection, which is very important for us in this meta-classifier. So we use different type of feature selection techniques, correlation coefficient, genetic algorithm, tree-based method, and also filter-based. But here in this meta-classifier, we use correlation coefficient technique, and also we use a genetic algorithm to select the best set of features. So just to explain the meaning of a meta-classifier, in Ensemble, a meta-classifier is a higher level model that is trained on the output of the baseline model. Here you can see that we collect the network traffic data, we dump these network traffic data in pcap file, and we have to extract what we want from those network traffic data. And this is the original feature. As I explained, we have feature conversion, feature normalization, feature reduction, feature selection. And we have at this step, we select the best combination of the features to train the machine learning classifier. And here, in this meta classifier, we use 3 different techniques: XGBoost, here, random forest, and XGBoost is an ensemble learning, which uses boosting, and random forest also is an ensemble learning, which uses bagging. And also we use a different type of classifier, which has a structure of neural network, multi-layer perception. As you can see, based on the output of every classifier, we again do another training, which is not based on bagging and boosting. It is based on stacking. So, and we have a detection phase to distinguish DDoS attacks among benign, and also we have a classification phase to classify different type of the DDoS attack. And so how to this is the result of the meta classifier. As you can see, it took like more than 2,000 seconds. It accurately identify the DDoS attacks, but it takes too much time. So we tried different experiments to reduce the training time. Here we can see we use all samples and non features, as I mentioned in the previous slide. And here we use all samples plus just 8 features based on genetic algorithm. It used just approximately 1,364 seconds, but still we have 100% accuracy. And here we used undersampling plus all features. It took just 55 seconds. And we can see that again, we were able to accurately identify the DDoS attacks. And also here we used undersampling for just 30 features, which was not good as compared with the genetic algorithm here. And here also it's for the classification phase. As you can see, we use like all samples of all features. It took like around 5,000 seconds. And here, when we use all samples of just 30 features, we reduce the training time to 4,000 seconds for classification phase. This is a comparison of the meta classifier I explained in the previous slide. And the conclusion, just to some important points about the transfer learning and ensemble learning. Transfer learning can address data imbalance, as I mentioned. We can train the model based on a data set that we have enough data for all the classes by leveraging pre-trained model, which was trained on a balanced data to improve the performance of the model on an imbalanced data. And knowledge transfer improves the model's adaptability by leveraging existing knowledge, features, and domain expertise, making it more capable of adapting to new tasks quickly and effectively. Transfer learning enhances performance optimization by reusing valuable features, accelerating training, reducing data requirements, improving generalization, and adapting to new domain and fine-tuning for task-specific improvement. And also for the ensemble learning enhances generalizability by combining diverse models. I mentioned you can use different type of the classifier, reducing errors and improving robustness, resulting in a better performance in unseen data. And these are some references that we used. Thank you very much. And I don't know whether we have enough time for questioning. Otherwise, you can contact me via this email.
Yeah, thank you very much, Mahdi, for that interesting topic and also interesting insights into the research of ML and deep learning as well. Thank you very much for joining with us and have a nice day.
Thank you. Bye-bye.
Bye.